Hey ladies and gentlemen, I'm Faris Ammar Kuzay, studying at Istanbul Kultur University Civil Engineering Department, and I was assigned by Dr. Ahmed Aman bin Dawn to calculate the bucklings, deflections, shear moment forces, normal stresses, shear stresses of a two-story building made of timber. Now this project is for the term project of Strength of Materials 2. We are a group called Group Zeta, made by a couple of members, me, Faris Ammar Kuzay, Yatijan Serdar, Muhammad Birhim Elif, Muhammad Elit, Sina Serozon, Dokan Dijur. Moreover, first of all, I will make a small introduction about the project. Now in this project we have some given stuff about it, which is the material properties, the sigma wood, which is 700 kg per meter cubed. We have section dimensions of the members as the following. We have columns with a dimension of 30 times 30 centimeter at the ground floor and the first floor. For the primary beams, we have two types, the T beams in the middle and the L beams on the edges. In the primary beams, we will have 4 primary beams in the first floor and 4 primary beams in the second floor. For the second beams, we will have 9 secondary beams. Then the dimensions will be 10 times 20 centimeters. We have slabs, which is the dimension of 10 centimeter. The deflection of the beams, as you can see in the picture, are limited to 1/360 of the clear span. Now in the Zeta cube, we will have some parameters which are given to us, which are the dimensions L1 8 meters, L2 9 meters, H front 7 meters, H rear 4 meters, Q1, which is 200 kg over meter squared, Q roof 50 kg over meter squared. The dead load factor is 1 and the life load factor is also 1. Now for the project calculations, we will calculate what's given, what should we calculate, which is the N and V diagrams of the simple beams, the primary, secondary, the critical section analysis of the columns, maximum normal shear stresses, and we have to check for the yield point, for the safety, for the stability of that building, if it can handle or not. Now I'll show you a 3D diagram of the project that we have. As you can see, here we have columns, which are circular columns. We have primary beams, those are the primary beams. As you can see, we have 4 primary beams. In the secondary beams, we will have 7 secondary beams and 2 from each edge, which makes 9 secondary beams, as you can see. Now let's go for the calculation of the project, which me and my teammates we did. First, we will calculate the secondary beams. This is a simulation of the secondary edge beam. As you can see, dimensions is 9 meters and the length is 9.6 meters, because there's a difference in the L1 or in the L2. Let me check here. This is the L and this is an extra length that we have to calculate. In the first floor, we're gonna have the Q roof and the Q slab and the total load. As you can see, here are the calculations that we made. and there's gravity which is 9.81 that we did, and we found the numbers in Newton. And here are the secondary middle beam of the first floor that we did. We have here the pin supported and roller supported. We found the moment at A, we found the Fy and the shear and moment diagrams. As you can see, we have the V maximum, which is 49.35 kilonewton, and the moment that we found the maximum, which is 94.75 kilonewton times meter. Now we calculated the first floor secondary middle beam. The M maximum that we found, as we said, the 94.75, and the V max 53.46, and we have the moment of inertia, which is 6.67 times 10 power minus 5 meter power 4. We have the T, the width of it, which is 0.1 meters, the Y 0.1 meters, and the Q 5 times 10 power minus 4 meter cube. Now we calculated the normal stress and the shear. The normal stress, the equation of it, which is My over I, as we all know. M, as we found from the diagram, is 94.75. The Y, which is 0.1, and the moment of inertia, which is 6.67 times 10 power minus 5. And our answer, of course, for the normal stress, it's in megapascal. Now, here we calculated the shear, which is, as we know, the formula VQ over IT, and we found this answer for 0 megapascal. And now we are calculating the secondary edge beam of the first floor. We have double load W1, as you can see, and W2, and we calculated the moment for them, and we found B2 and A2, and those are the diagrams for them, the shear and the moment diagrams. We have the minimum here, which is minus 28.73, and the maximum shear, which is 26.52. For the moment diagram, our maximum moment will be 50.92 kilonewton times meter. For the primary front beam of the first floor. Now for the primary front beams of first floor, we have those which comes from the effect of the slab load, the dead load factor, the life load factor. That's why we subtract, and it goes down, as we can see in these pictures in the shear diagram, and also for the moment. For the first floor primary front beams, we can see we have a T shape here. We found the moment of inertia, the Q, the normal stress, and the shear. And for the primary back beam of the first floor, it is symmetry. We found A3 equal B3 here, as you can see on the shear diagrams, which also have an effect of the slab, dead load, life load, and so on. Now we will calculate for the primary edge beam of the first floor. We have 3 loads, distributed loads, W1, W2, and W3, as we can see, and we made the calculation for the shear and moment. Now I want to show you for the primary beams. As we can see here, those are the primary beams here. We have 4, as we said, 4 primary beams, and those are the secondary beams, which are in yellow, as you can see here. This is the front side. Let's continue now for the first floor primary edge beam. We made also those calculations for the stress and shear. Now for the columns, we have the self-weight of the column, and those are the calculations for them, which we calculated in newtons. And also here the self-weight of the column, And now the first floor back columns. As you can see here, the shear and the moment they are 0, we don't have. We found the P maximum, which is 1413.71 kilonewton. And for the first floor front columns also, the shear and the moment are 0. And we have the buckling, which is the most important for the columns to check its stability and safety of it. We did those calculations, the Py, the P critic X, which is equal to P critic Y because of symmetry, and we made the calculation for the P max for Py, P critic Y and P critic X, which are all equal to each other. Now for the ground floor, each one will have a distance of 1.125, the total distance, which will be added. Now for the ground floor, we made those calculations, which we need the Q slab of it. Now I'll show you in the 3D dimension. This is our ground floor here. Those columns are from the front columns. Here we have the primary beams, the front ones. Here are at the back primary beams. Here we have the edges. We have two edges, as you can see in the 3D warfare. And also the columns, they are angled columns, as you can see. Yeah, like this, they are angled. Let's continue now. The ground floor, the second middle beam. We have two loads, W1, W2. We did the diagrams for the shear and the moment. We have the maximum shear, which is 32.40 kilonewtons, and the moment, which is 64.81 kilonewton times meter. Here, as you can see, there are the calculations of the ground floor secondary middle beam. We found the moment of inertia, the Q, the M maximum, as we said, and the V maximum, and we found the normal stress and shear. Here are the ground floor second edge beam. As you can see, we have the K factors, K1 and K2, and W1, W2, and we found for the shear and moment diagrams. And here are the calculations for the ground floor primary back beam. We have pin support and roller support, and we found the shear and moment diagrams. Here we, of course, they will have an effect of the slab, life load, and dead load factor. And now we are at the calculating for the ground floor primary back beam, which is, as you can see here, the ground floor, the back, like this, as you can see. And here we have an L shape. We found the moment of inertia, the stress and the shear. And for the ground floor primary front beams also, we calculated the shear and the moment, as you can see. And now the ground floor primary front beam, which is equal to ground floor primary back beam. We found the stress, normal stress, which is 30.873 megapascal, and the shear, which is 1.768 megapascal, and the ground floor primary edge beam, which where the maximum shear will be 3.85 kilonewton, and the maximum moment, which will be 7.69 kilonewton per meter. Those are the calculations for the ground floor primary edge beam. The normal stress, which is 787.92 kilopascal, and the shear, which is 57.82 kilopascal. And here are for the ground floor front column. We have the self weight of the column, which equal to this number, and the self weight here. Here are the columns, which, as we said, it's angled, which has an angle of 15 degrees. And here we have the BF1 plus and the BF2, which are the loads on the column that we have. And here are the ground floor back column. We have the self-weight plus the self-weight of the column, which is 700 times the unit weight 9.81 times the area times 4.50. And here are the ground floor front columns. As we can see, we did those calculations for the normal, shear and moment diagrams. And now for the buckling of those columns, which we are concerned with, the P critic X, and which will equal to P critic Y, which because of symmetry. And now the ground floor back columns, we did those calculations also for the normal, shear and moment, and the buckling, which we found the P critic Y and equal to P critic X, which is equal to this number in kilonewton, and the Py, which is also equal to this number in kilonewton. And now the first floor secondary middle beam. In this we can use the energy method or the integration method. Here, as you can see, we used the integration method, which made integration, and we add to constants C1 and C2, and we want to find the maximum deflection that will occur, which here we found 0.863 meters, which is too high. There are 7 same type of secondary middle beams, so they have all the same deflection, as you can see. Now for the first floor primary front beam, we also want to calculate its maximum deflection. We use also the integration method. We have the V maximum, which will equal to 5.42 times 10 power minus 3 meters. And as a result, as we can see, we have two different types of beam. One of them is the simple beam and the other is the overhanging beam. And the only difference will be the numbers, which will make the suggestion about it at the end of our project. Now the ground floor beams deflections. We have 7 types of beams. Now the length of that beam is 8 meters, which of course is too high for a temper beam, and we will make that suggestion at the end of our project. The maximum deflection is 1.025 meters, which of course is too high. And here the primary back beam, which will equal of course the primary front beams, they are all the same, which we found the maximum deflection of 12.78 millimeters. It's quite normal for this deflection. And here the primary edge beam, we found its maximum deflection as 10.13 millimeters, which is also quite normal for it. At the end of the project, after we made all those calculations for the deflection, for the buckling, for the normal, shear, moment, forces, diagrams, and also the calculating secondary beams, primary beams, and so on, now we will make the suggestion about this building, which we know that the normal span length of a timber is between 5 to 7 meters. Ours, in our project, it's 9 meters, which is too much for it, and the deflection of course will be too much in that case. So what can we do is to change the dimensions, like to change the length of the span to make it 5 to 7 meters maximum, and the Q, the life load is heavy also, we can change the life loads. And in addition, the moment of inertia of the cross sections are not sufficient to prevent that amount of deflection. In order to decrease the deflection, as we said, change dimensions or the shape, the area of the cross section, and that's it. And that's the end of the project. At the end, I would like to thank Dr. Ahmed Anal Dindar for this kind of project, which is really important and sufficient as an engineer. I learned a lot on how to calculate the deflections, the bucklings. It was very useful also as an engineer to know if those kind of projects like the timber buildings, if it can handle too much load or not. I also want to thank my team members for all the support that they did and all the hard work that they had done for this project. And thank you very much for listening to me.